the probability of Z1 given X technically comes from a Gaussian with this mean and this standard deviation, right? So this is a Gaussian over Z1, where the mean is basically 1 over E1X, and the standard deviation is technically just beta 1. Okay, so, and this technically is beta 1I. Why? Because if you think about this multiplying this becomes beta 1I. Do you want me to close the curtains? Yeah. And same here basically goes for the second one. For any other basically t given previous value that comes from this Gaussian. Beta t I. So that's the idea of like a forward diffusion. We also talked about that, well, there is a challenge here is that if you do forward, you need to sequentially go through all of this. So there was this idea of like using a kernel trick basically. And the kernel diffusion basically says that if you are trying to, if you think it's kind of like this is a recursive function. Every time this zt comes from the previous function. So if you replace that, you can basically define alpha to be 1 minus alpha t to be 1 minus basically, alpha 1 becomes 1 minus beta 1. Then you can define something called alpha t, becomes multiplication of this j from 1 to t. Right? And using that, the kernel trick basically becomes like you can calculate any z at any point directly only using x. You don't need to know previous z values. And that basically is alpha t plus 1 minus alpha t times some epsilon. Sorry, x. There's an x here, and there's epsilon here. So that means at any time stem, you can find the noisy version, like you can estimate like a 10 step ahead by just simply having the input, because you know the schedules. Apply the schedules, that becomes the mean, and then you sample some simple Gaussian. So that becomes your variance. So that means probability of zt given x comes from this Gaussian with alpha tx and 1 minus alpha ti. So this was the idea of the diffusion kernel, and it helps a lot in the process. Now, so let's look at the probability value. So we have a posterior distribution, we have a likelihood, and we also have basically prior, right? So
can you explain what are posterior and prior here?
In general?
No, just for this diffusion thing, like I don't have any picture of it.
So prior is think about it like, so in the concept of the diffusion, the posterior is when you do reverse, technically, when you do reverse Gaussian, reverse diffusion. So I want to understand what is the probability of zt minus 1 given I have zt, when you do reverse. So I have a total noise, right? And I want keep going until I want to get an image, correct? So at this timestamp, let's say this is zt, t minus 1, this is t, because in forward the timestamps was defined. This becomes the posterior probability, this given you were on the previous one, correct? And this basically we know that technically comes from the Bayesian, comes from probability of zt given zt minus 1 times probability of zt minus 1, correct? So this on the left is the prior. Basically, it tells you that what is the chance of, in general, being in having the zt minus 1, like the prior knowledge. And you basically can assume that by default, in this definition, this is interactable because you cannot calculate this, right? This prior, this term. probability of ZT minus 1. Technically, you don't have it directly. It's intractable. This term, we do have it. It's here, right? No, actually, it's here, right? This is the likelihood one, right? This comes from the forward. So you need to calculate basically this now.
That is posterior.
That's the posterior. That's in the reverse direction. So the reason we go toward Bayesian is because when we want to go reverse, we're like, well, what's the easiest way to do that? Well, Bayesian framework. If you have these two, you can estimate that, right? So the does that answer? All right. This time being. Now, let's look at the PZT, start with the marginal, probability of ZT minus 1, right? So this technically means, if you think about the idea of diffusion, again, you start from an image, you go all the way to pure noise, and then you want to go backward, correct? So the process is stochastic in general. So when you go from here to here, in every step, if you repeat one step, that means if I go from time t to t minus 1, and if I repeat it again, I get a different one because it's stochastic. It had some randomness in it, right? So if I want to understand what is the probability of this, like the marginal probability of that, that means you need to technically calculate all possible ways that you go there, not just one go, right? Because if you repeat, if I'm here, one step to here, in every time, if I just repeat that one step in a loop, every time is a different answer, correct? So there are all possible scenarios to go to that direction. So again, you can think of this as, we will see this image later, but if you go from here to here, right? This pass is one time effort. If the next time for the same image you repeat this, you might go something like this. You might go something like this or something like this, right? That's the reality of it. It has a boundary, but it's all possible ways to go there. In the reverse scenario also, it's the same thing. Like it could be any basically types of latent variable that it generates for you. Again, they all have boundaries because you know the mean and kind of like the variance. But that means that if I want to understand what's the marginal of this, I need to calculate it across all possibilities. Possibilities over what? So you need to find what is the basically probability x1 through, let's call this t, xt, z1 through zt, and x, dx, dz, right? Because it's a joint distribution across all possible. And what do we know about joint distribution in diffusion is Markovian. Probability of z1 to zt and an x is technically probability of x, z1 given x times from t from 2 to the end, probability of z t given zt minus 1. It was a Markovian property. Every time step only depends on the previous one. So it's multiplication of all possible probabilities. So that is this term, correct? So this is like z and x. Now, why x? Because what it tells you that if the question you are asking, what is the marginal of a given hidden state? Something here. That given hidden state, because it's not just for one x, it could be for any possible x. And it could be for any prior z also. It's kind of like has basically a stochasticness in it. So you need to calculate this marginal over all possible x, that it was the starting point, and all previous z values that you could see in order to calculate this term. The problem with this term is that, as I said, this is untractable. If you cannot calculate all of them, that becomes a problem. So one of the ways that we could simplify this problem was that I removed the wrong one, but anyway. So if you think about this term, this is Markovian, multiplication of individual, basically Markovian probabilities. But one thing we know, if we use diffusion kernel, I don't need to know possibilities all previous z, because I can calculate in one shot, right? So if you are using, see, if I use this definition, that means that let me change this x z. Technically, instead of having this with respect to z, I can just use a diffusion kernel. So this becomes for all possible x, probability of basically z dt given x dx. Sorry, there's a probability of basically c1. Now we ct, yeah, just need one. So because this becomes like using the kernel diffusion. Now, so this means that we couldn't calculate this directly. So we did a trick. We condition it on x instead of with respect to all z's. So this term will change to given x. Okay, so that means you're finding this marginal, but using the basically diffusion, the kernel version. Okay, does that make sense?
I didn't really understand how that final equation, the second equation went to the third equation. How did that?
How this went to this?
Yeah.
So in order to calculate this across all possible z,
Yeah.
right? Why do you need to calculate that? Because you want to sequentially go through time. So if I give you a formula that from here gives you the end, do you need to calculate this? That's the diffusion kernel. So the diffusion kernel says that you don't need to depend on the previous time stamps, not x, previous and hidden. So you can just use a diffusion basically kernel function, which is this one. And that itself is this Gaussian. That's the Gaussian, right? So we have a Gaussian here. We have a Gaussian here. We basically mix two Gaussians, which we talked about in previous class. So you come up with a new, like a mixture of two Gaussians, basically like a combination of two Gaussians. You find a new covariance, you find a new mean, and then you can find probability of dt minus 1 given zt, right? Which this one was, write that. This term is itself a Gaussian over so when you mix this Gaussian and this Gaussian, that's a new Gaussian that you will get.
So that ZT given X is for the encoding process, right?
ZT given X.
No, the above, yeah, this one.
This equation.
Encoding process, right?
Yes.
That one is decoding process.
No, this is
We
decoding.
don't have it, but
This is decoding.
yeah, that
These
is,
are encoding. ZT given ZT minus 1, that's a forward
yeah,
process.
but that's just the Bayesian equation.
Right.
That one on top, that is equates to P of ZT given X. That would still be encoding, right?
Now, so, okay, let's understand what we are trying to do here. You are trying to find a marginal of Z, that value.
Yeah.
what we are saying, in order to find marginal of Z, instead of going through all steps, in order to find this value, this is what you need to do. This is a bucket of images I have. One at a time, I pick one image, and I say that for this image, give me probability of ZT given this image one in one go using that equation, right? The diffusion kernel. Then I pick another image, right? So you repeat it infinite time, correct? Combine these Gaussians, right? That becomes the marginal of ZT. So that's the meaning of that integration, is that you want to see that what is the general probability of ZT. So previously, you needed to calculate this times all possible ZT minus all possible, basically previous steps. When you use the diffusion kernel, you get rid of all of this, and you just do one shot using diffusion basically kernel. And then now you need to sample it because it's an integration, or you need to do across all possible X from your data sets. And then that's how you get the probability of ZT. Right? So this part is technically, it's learned during the forward pass, during the training, because you have lots of data keep coming through, you learn this over time. And then you use it in the backward process. Right, so this basically comes from your training. Does that answer your question?
Sorry, just a
Yeah.
small question. So the first equation is integral of P of
Z1, Z2, Z2,
all
Z,
Z and X.
and X. It's a joint distribution.
Okay, so the next one shouldn't have the P of X multiplied by the P of Z of T conditioned on X. So there's
Yeah,
another
actually,
term.
there should be, you're right, there should be a P of X, D of
Yeah,
X, great. P of X, D of X, great. The starting point.
Thank you.
Thanks. So, does that make sense? So it's just, this is technically all it tells you, that sample all possible images. And for every ZT, you need to have some sort of like a marginal. Okay. So, this is the term that we have now, this Gaussian, in the basically backward process. And in diffusion, what we talk about is that the only thing that you learn is actually during backward. During forward, there is no parameter, there is no model. Everything is predetermined. You have betas. From beta, you can find all the alphas. And epsilon is just random noise. So there is no learning in it. During the backward is what we want to learn, how to denoise the data, or basically how to make the data basically back to original. So if we know the probability of Z given ZT minus 1 comes from this equation, now we should be able to basically answer this, what's the probability of an image? And the unfortunate part is that the probability of image is step by step. You need to go all this. That means if you start from pure noise, you need to do one step at a time until you get to the image. And what we just found, this equation gives you the intermediate probabilities along the way. Okay, so if I'm at time t and I want to go to t minus 1, what I will say is that the image generated at time t minus 1, the denoised version of an image, is a sample from this distribution. Is it coming from a Gaussian? Okay, that means, again, if I am at time t, it's kind of, there's a human, there are lots of noise on it. And I want to go to the next one, which is still should be that human with less noise. In order to go this, you need to sample from this distribution. Right? You sample from some distribution, and in reality, we actually add an additional noise to it in order to make it more generalizable. Then this becomes this one. Then if I want to go to the next step, I would first find this. For the next step, given this, and then sample from it, add a little noise, go backward. Right? So probability of a total image, probability of an image in the reverse process comes from probability of the starting point, the pure noise, because the starting point is just a pure noise, like you sample from a Gaussian, times probability of the last step, x given z1, times probability of t from 2 to t minus 1, probability of zt minus 1 given z. That is t. This is t minus 1. Right? This becomes so this 2y, they're out because this one is a different distribution. Like it has a different equation, and this one is just pure noise. It doesn't need to have this equation. It's just pure noise that we generate. So that's how you, in the reverse process, when you go all these steps back, now you have one image. And if you want to see that, how realistic is that image, like you want to see what's the density of this image, comes from this equation, multiplication of all probabilities you created along the way in the backward, basically. Does that make sense? Yes. All right. So now, if you think about this equation, so what this is mean, this is variance, right? The only part which is unknown is the mean. This is predetermined. You know beta and alpha from forward process. Okay? Beta is the schedule, right? So I don't need to technically focus on this if I already know all the variances. The only part which I don't know is mean. Why? Because mean is depending on ZT, and ZT gradually being generated. So you don't know the mean along the way. That's why the first version of the diffusion model was, let's predict the mean. Instead of trying to denoise, we just predict the mean. At every step, I will compare this with the actual mean that I used in the forward process, and try to basically reduce the distance between those two. So what we basically say that in the first version of the diffusion, because we only need to predict the mean, let's get away from this equation and use a neural network to predict it for us. So we replace that with f theta z, or f theta, basically, yeah, zt, and have x and just use one parameter. Right. It's just a neural network that gets a couple of inputs and it predicts the mean for you. And our basically loss function becomes comparison between the result of this neural network, which is the mean, and the actual mean that we have. So we train in the backward process. You have a loss function. You basically train that loss function to, you basically reduce that loss function with respect to the parameters. And your goal is that to find the best parameters along the way. So that means we want to go here. So if, let's say you have n data points, n images, right? So probability of x, like entire data set, comes from the multiplication of, so I from 1 to n, p of xi. And p of xi for every image is this. This is during the reverse process. So this is the likelihood term, correct? And what's our goal is, and we know this likelihood term basically is with respect to some parameters, technically, phi. So our goal is that, because the phi is predicting the mean for us. So our goal is that to find phi1 through phi t, all the model parameters along t steps, which is argmax for all phi's, basically 1 through t, this term. Similar to any other modeling that you have seen, it's just a likelihood maximization, right? So you maximize this likelihood to find these parameters. Or you can directly minimize basically the divergence here. Whatever the model predicts as a loss function. So you can, this is similar to argmean basically, if you use this loss, f theta z, let's say t, minus ut. So always we have seen that the maximizing the likelihood equal to minimizing the basically loss, right? Does that make sense? Questions on that? Ask it.
So, the f of phi is the mean of Gaussian for.
A bit here. It's the neural f. Here's the timestamp
Okay, okay.
because you go gradually, right? So f of f is a function, is a neural network, right? This neural network gets a couple of parameters as an input, and it just gives you a vector if the dimension that you have or a number, correct? At every time step give you that. That's why it has a t as a parameter, basically, because it depends. Every time step, actually the parameter is different. So it gives you a mean value, and you already knew during the forward what was the mean that you added. Or actually, you can also directly use this to exactly find the mean and just compare it. So if you think about during the training, what's the goal? So during training, you have the data, you have the knowledge, right? So I can calculate all means as a true source. Like this is my true value, target. And I want to train a model to predict that. So your goal is that I already know that, but I don't want later during inference to need to calculate this step by step, right? Because you need to always keep track of things. So instead of that, I will train a model to predict that for me. So that becomes the total overall goal, that you have to train a neural network that can predict this value for you.
Okay, during the training, you were saying that we can go one step, no step by step, just one shot. And so if we go one shot, we don't know the exact minimum of each mean value of each step.
But during backward, you need to go step by step, correct?
Exactly. So what's the mean, like mu over there? Do we know the mu?
This is the mean. This is the actual mean.
This is f that we want to
No,
find.
f, we are going to use f to approximate that. This is not f. This is the true target, the target, right? This is the actual equation, and it doesn't matter if during training you jumped 10 steps. During backward, I exactly can predict what was the mean, because the equation is fixed. What I'm saying is that instead of doing this, you already know it, right? You have your data set, you already know it. So during the backward, where you're training a model, you've trained a model to predict a number. Let's say your model just say 5, and you compare 5 with whatever this equation gives you. And you tell to the model, update yourself because you're wrong this much. And you keep repeating that process until the model learns to predict this.
What are the inputs to the network?
Inputs to the network. So the learning is during the backward, right? So input is pure noise. You start from a noise. Okay, so let's say, so this is during backward process. So we say ZT comes from pure noise. Okay, then you want to find ZT minus one step. We know that comes from a Gaussian with this, basically this parameters, mean and standard deviation, random sampling from this Gaussian. Okay, that's why random, because again, if you remember, the trajectory is all possibilities. At least in this version of the diffusion we saw, you could go, this is a random sample, you could go any path. So you sample from that Gaussian that we saw the equation here, right? And then in reality, we actually use some sampling thing, like we come basically to Langevin. Langevin basically says that, well, we also add some noise to it because we are not exactly sure if this sample that we have is on a correct trajectory. So we kind of add some noise to make it more generalized, right? So you basically calculate this one, but during the backward, what we are saying that the goal is not to just do this, but the goal is that whatever is this mean, predicted using a model. So I know I can calculate it this way. I know that. That's hard. That's just a sequential process is slow. In order to improve it, I will train a model to also give me that. So later, when I'm done with training, I don't need to calculate that. I just basically say the mean is f phi, whatever is the value, and the standard deviation is basically something fixed. So here we're going to talk about what I say basically something fixed. Here, right now, this is a standard deviation, correct? Yeah, let's assume you have some standard deviation.
What are the inputs to the model?
The neural network is asking for the.
To the network.
ZT, previous timestamp,
DT at any time,
previous timestamp.
previous time.
During the diffusion, the reverse diffusion, you don't jump. You go one step at a time. Actually, the steps should be small. If you want image quality to be high, you need to take steps a lot and slow. During the forward, we don't care because we can estimate it to go to pure noise. If I know beta, I can just estimate it in one go. During backward, that's why we don't have a kernel process in the backward, because we need to go, because think about it. If you are here, pure noise, and then you jump there, you see some random image, how do you know actually if you would have gone through the trajectory, you would have get that image? Right, so you cannot jump because as we talked about it before and we will see, everything is kind of like a gradually adding to go towards some modality. Because if your data has some distribution, all possible data, and let's say this is modality for cats, and this is modality for dog, and this is modality for bird, and you start here, jumping one step doesn't make sense. Where do you want to go? You need to gradually let the data, let the distributions to pull you toward basically where you need to go. Wherever you are closer, you basically end up going there. It's kind of like a random, at least in this version.
The input to the network is ZT
ZT,
and X.
time. So here, technically, there's a, technically, if we do this, we don't actually need X. We just basically, we don't have X doing backwards. So you just ZT, previous timestamp, and a T, and the parameter. That's good. The parameter is not an input. You write it down. So just ZT and time. Time need to be embedded along the way in the model input all the way.
My question might be repetitive, but I just want to understand here, we can calculate this directly, the 1 minus alpha t minus 1, but we choose to do the neural network part just so that during inference, instead of doing this, we can get it predicted from the neural network, the mean.
Actually, 1 second. Might have one typo over there. Give me 1 second. Is a missing, actually, yeah, there is a missing term over there, total. When I moved it from here to there, I actually didn't add the full term. There was, so, I'm going to this. The mean, if you remember, when we combined the two Gaussians in the posterior was likelihood times prior. So likelihood times prior was with respect to X. Remember, we did the integration over all possible X. There should be an X in the equation. So plus, technically, alpha t minus 1, beta t over 1 minus alpha t x, and then this is the variance, the same thing. Sorry, I've dropped that term. So that, again, this was the mixture of two Gaussian, likelihood times the prior. The prior was ZT given X, which was the integration of all possible X's. Right? Again, if you forgot this term, it was probability of ZT given X times probability of X, P of X, right? So that was the likelihood, the prior term, which is a Gaussian. Then we had a likelihood term, which the likelihood term was coming from forward, which is what is the probability of ZT given ZT minus 1. correct? Two Gaussians. When we combine these two Gaussians, we got this term, this new Gaussian, with this mean and this variance, correct? So we can always calculate this term because we have all of this. Right? During training, we can always calculate this. The problem that we have is that during the inference, if you think about it, one, I cannot calculate this during inference. You need it during inference. Why we cannot calculate it?
You don't have X.
Exactly. Diffusion doesn't have X when you generate data. It's just random noise. There is no X during the backward. So during training, instead, I can calculate this during training, but what I will do is I will say that, okay, I will find a model that predicts that for me, right? So now during inference, I don't need X. I don't have any dependency on X, and I don't need to have this directly to be calculated. I just approximate it using a model.
So that was my question. Because we have ZT available, we can calculate it even during inference. Then why do we need neural network in the first place?
So,
Yeah.
sorry, that was, I dropped that part by mistake. So yeah, there is an actual X over there,
Yeah.
dependency on X.
This does not allow us to control what image to generate right now. And
We'll get there.
So like when we're calculating the loss function, calculating the difference between the neural network's
And this
output,
term,
that term is the mean obtained in the
basically
encoding.
during the decoding, but in training.
in training.
Because during the training, I have data, I have all of this.
Okay.
When you train, you have a sample, you just generate, or you go forward, backward, so you have to have the data. During inference, I don't have data. I just want to pass a total noise to a model and give me a basic image.
The reverse of the training, the batch, what's confusing here? The batch propagation of the network is confusing me with reverse thing. Like, when are we training the network?
Okay, let's just clarify a couple of terms. When we say forward and reverse, forward means I have an image.
Making noise.
Yeah. Totally goes to noise. Reverse means I have this noise, I want to get the same person. It's kind of growth over time, right? When you talk about training, ignore this, ignore the forward, backward process in your mind, flip this in your head, right? Put this one here, pure noise, to image, right? Does that make sense? Do a forward, backward propagation. This is X in your head. This is label.
This is ZT.
In your head, make it X. Doesn't matter. During the inference, call it B, call it J.
No, I mean that noise ZT is not X, isn't it? I don't know.
Okay.
There are already a lot of nuances in my head.
ZT, X, correct?
Yeah.
Forward, backward. No, neural network. Forward propagation, backward. Ignore all of that. We're just right now talking about this. Isn't it clear, everyone? The idea of forward, backward here? No? It's general neural network. You just flip the idea in your head. This technically you don't even need to flip, because in reality, this is, if you look at the papers, this is basically how it's defined. This is one straight training. It's not that technically reverse. We do reverse so it's easier to follow. So there is no learning here. From this point to this point, there is a model. You want to train that decoder. There's no encoder. You want to train a decoder. A simple, like you can just do a gradient descent. Stochastic gradient descent, something like that.
The training of that neural network during decoding process happens from ZT to X or ZT to ZT minus 1.
Z, all of this along the way. At every time step, you have a T parameter, T here, BT. Every time step has a different parameter.
From when we go to ZT to ZT minus 1, we predict and try to get that mean accurately, and then we move to ZT minus 2, right?
That is correct.
Not
You do one step at during backward, you don't jump. You actually take the really small steps because it's stochastic. You want to generate image, you don't want to ruin the quality. So you need to be sure that the model, because think about it, if I take a bigger step, really large step, and you're like, wow, you're off by this much. I don't learn what was my mistake along the way in order to improve the image quality. But if I take really smaller steps, you tell me, okay, how much wrong you were? Okay, I'm like, okay, I'm going to do this. So next time the image quality is better. You need to take really small steps with respect to what was your previous timestamp, T minus 1, go to T minus 2, so on, until you get to X or basically T0. Yes. I never thought this going to be this many questions, but go ahead.
Like when we say like we cannot control what the model is generating up during the prediction. So for that thing, is it necessary for a like same noise at same time interval? If you feed into the model, it would generate always the same output, or
If you pick the same noise, pass it to the same model, it doesn't exactly give you the same, but most of the time gives you the same answer. Same noise. You don't, why? Because the model, if you're in some space, the model goes toward the closest class possible that is there. With a little, if you think about steps, maybe a little left, right, wrong, but it will go to the same direction. But if you reinitiate, like a rerun your model, which basically generates a new starting point, every time you get a different basically image, depending on where is your initial point and which class is closer to you. This is a version, again, unconditional diffusion. We don't have any prompt, we don't have any class, there's no injection. It's just random, let the model go toward what is closer. All right. I'll let you last question, then we continue.
I might be backtracking a bit over here, but we have an image, we encode it to get noise.
Mhm.
Then while decoding, we are training the neural network to against the mean. When is that mean calculated? Because right now we're training, right?
Just during your backward process, it's kind of like you're writing a code, right? In your code, just calculate all of this.
Yeah.
It's a ZT. You have this, correct? You have the beta. This is one equation.
Yeah.
Why you cannot calculate this?
before passing through the neural network, you can calculate that and pass them.
No, even during backward.
Yeah, backward.
If I know ZT, which is this one,
Yeah.
and I want to go one step after, why you cannot calculate this value?
I think because I don't have X or
During training, you have. This is during training.
Okay.
You have a pool of images, X.
Okay. Got it, okay.
During inference, we don't have X. We want to use this to get away from.
Okay, got it.
All right.
Yeah.
Okay, I'm going to pass from this. Hopefully, you guys will review the materials next time for yourself. All right. So, okay. So this was. Now. Okay, so one thing we're going to just talk about is called variance preserving. Okay, so the version that we saw here, this version, is actually the general term is DDPM, denoising diffusion probabilistic models. But this version is called variance preserving. So it's common if you see VP diffusion. Whenever you see VP, that means variance preserving. Variance preserving means that, along the way, that's, the variance basically is preserved. It's like you're not basically ruining it. You basically, you kind of shrinking the signal. You start with an image, you go to a pure Gaussian, which if you think about, if this is your original image, all possible modalities, you shrink that to go to a just simple Gaussian. So it's kind of like a shrinking process, right? So this is called variance preserving. Now, one thing that we saw was, okay, well, this version of variance preserving is focusing on the mean, calculating the mean. In reality, the quality of images are not that good. Okay, if you train it with respect to mean. So what happened here is that the next version of the diffusion, basically when it came out, was, let's say that instead of focusing on this, let's focus on the noise concept. Okay, so why noise? Because, and this becomes the denoising version technically. So if we know that ZT basically is calculated from 1 minus alpha T x plus alpha T sum epsilon, right? And epsilon is technically the noise that you have added. The rest of it is known, right? So epsilon is the only part that, you can say the epsilon is technically, that's the sample, the stochasticness that you basically had during the forward process. So we can rewrite this. Basically, you can calculate x, which becomes dt minus alpha t epsilon over dt minus 1, sorry, minus 1. So, so you can calculate x. You can also calculate epsilon. Epsilon, like the equation for epsilon becomes dt minus 1 minus alpha t minus 1 x. Actually, I think this was alpha t or t minus 1 we wrote before. I think t, but let's review it. Yeah, this should be alpha t because we can't estimate it exactly. Times, sorry, it was this term is multiplied by x and then divided by, that's the epsilon, correct? That's the noise. So the only part that we are technically changing along the way, that's like kind of like a stochastic, is that epsilon, right? You agree? Okay.
All of this, yes.
So the idea will be that instead of focusing on finding mean, let's focus on finding this epsilon. So instead of basically training a model that predicts mean, you train a model that predicts the epsilon, basically the noise, right? But the idea here becomes that we need to keep the variance, basically we assume that there is a variance is fixed. So in this version, this variance, basically we assume it to be a fixed value. So we basically try to train a model called GT, or G phi, basically, that has ZT and time, and this basically going to gives us the noise, basically that, which is the variance technically. Does that make sense? So in the forward, you keep adding this, right? This is a fixed term. So this is coming from a Gaussian. If you multiply this term by this, right? So wait, I think there's no square root there. No one here corrects me if I make a mistake, but the views or let me see. Oh yeah, okay. So
but it's,
Opposite.
yeah,
Yeah, but it's
alpha,
Alpha
and then
T
one
X
minus.
and then.
Yeah. All right. Now it's better. Thank you. So now this becomes reverse. So alpha t becomes 1 minus. And this becomes 1 minus. This becomes alpha t. So the idea becomes that instead of trying to find mean, we don't train a model to find mean. We train a model to find this. And this is the variance. What does it mean this is a variance? This is equivalent to technically this term, the variance. So we will find the basically we will say that the mu phi, when you say mu phi, it doesn't matter. That doesn't mean that we have another model. Mu with respect to a parameter. Okay. So mu phi comes from somewhere I wrote this. We can write it as 1 minus beta t. So what we are saying here is that in this version, the mean value of this process is calculated from this equation. And the only thing we need in order to find mean is a model that gives us this noise basically value. This is what we will predict. So instead of what you saw previously was to train a model that predict this, okay? We train a model that predict the epsilon, and we calculate the value of the mean using this equation. In case you forgot where this equation comes, it's all in your slides. Okay, to break down all the steps. That becomes the mean value, right? So that means in order to make this accurate, I technically need to find this accurately. Because it's the part that I don't know is the noise. So that's how the loss function basically becomes noise minus the noise that you actually added minus the noise that you predicted. So doing forward, you add noise, right? And you know the scale of the noise, for example. You can basically pick that. And then you predict it using a model, and the focus of the model is to train this model, this parameter, actually there's a t also, that means the parameters are also with respect to t, remember, to be able to predict this noise. By doing so, this becomes a denoising basically process, like a focusing on noise only. And that's where it becomes similar to the score-based model, which the idea of, if you remember, we had a score-based model before diffusion, was to add noise and to slowly predict the noise. So this, at this spot, the diffusion model and the score-based model, they kind of like have same flavor, so it becomes somehow similar. So now we can use similar techniques that we use in score-based to solve also here. I'll wait on that because I see. You always have question.
Always happens. Not this time.
Okay, good.
So just to confirm, this noise is something we added in the backward direction.
You add in the forward process. You added noise, you want to predict what noise was added.
So you keep track of it, how much noise you
So
added?
during the training, you always have data, you have the information. So you train a model to predict it. During generation inference, then I don't have a data and stuff like that. I just have a start with, so the idea would be the same. You will start with Z. which is pure noise. Correct? You pass that to this model and see that how much noise at this step was added. It gives you something, right? So you calculate this term, right? So this becomes the mean. Then you have a Gaussian. You sample from that Gaussian. That gives you, so sorry, if this is, Ashkan doesn't like this, ZT, and ZT minus 1 comes from a Gaussian with whatever is that mean, and the basically we keep the variance actually in this version fixed, which is called fixed variance. So basically you sample from that. Now you have second timestamp in the backward. This is during generation, assuming that you have trained that. Then pass this one again to this. Generate mu. Variance is fixed. When you say variance is fixed, it's with respect to theta. You remember there is a scheduling for betas. And then you pick another version and you go all the way. You repeat this until you get to the last step, which you need to calculate x, which basically becomes the probability of x given z1. And you sample the last image. So this becomes like a noise prediction version of the diffusion. No question.
So when we already could find the mean before, now why are we using?
Because the quality of the images were not good. In the version of the diffusion where the mean, you predict only for mean, the quality of images are not as good as the version that you go for noise prediction. So, okay, so these are like all basically variance preserving. There is there are two other versions. So it's called one is that learned. I'm just going to write it. Learned variance. So there is a version of the diffusion you might see, which in that version, you actually it basically focuses on predicting the both variance and mean using the same neural network. So you have a neural network, mu or f, with this parameter phi. This will give you two things, mu and the covariance at time t, at time t, time t. And then you repeat the same process using these two. Sample from a Gaussian with this, go to the next step, pass it to the model, gives you this, sample from Gaussian, go to the next step, and so on. So that if you see something like that, that's called this a version of the basically diffusion that you'll actually learn the variance along the way. Okay. Then there is actually another version that OpenAI has been using. It's called variance interpolation. So what they are doing is you still have the same idea. So you have a model that predicts variance for you, but they don't just use the variance that was predicted. They actually interpolate the variance. Like it's kind of like combining the predicted variance plus what you had before, some sort of like aggregation. So what they're using, at least based on what I found, is log covariance at time t with respect to actually parameter at time t. This comes from some learning parameter. Learned covariance plus 1 minus phi fixed. Okay. So they have this equation for combining the covariances. This V parameter is also something that you learned, is a parameter that you need to learn during training. And this fixed variance is defined as, sorry, fixed covariance defined as 1 minus alpha t minus 1 over 1 minus alpha t times beta t. Okay. So you have this fixed, which you always can calculate it based on the schedules. And you need to basically learn this. And this is a kind of is a log. So after you learn the log just to exponential, you convert it to the covariance. So this is a version that at least the released version that they are using.
There's no need of added noise in this, right? Because they already have a failure.
No, so during the backward process, you don't add noise. Okay, for sampling, language-driven sampling, you add always some noise because you want to be sure that you are kind of have some generalizability. But you learn the covariance and you learn the mean also, like you have a model. But for covariance part, they are using some sort of like interpolation, like combination of what you think it could be fixed plus what you learn. So you combine that. You have a model that tells you what it should be, and you have a knowledge that you think what it should be. You kind of combine those so to make it more robust. Okay, so these are all the basic ideas up so far. Yes.
I think you mentioned elbow or something like it went above my head.
Yes. So anytime you are any algorithm that you are trying to calculate log p of x, this is equal some summation over log px is correct. Anytime you have this, you can say that I know by default this is greater than equal than the elbow of the other side. So in diffusion, the same thing has happened technically. The during the denoising and during the this one version of the loss that you will see is technically it's you can optimize for that. You in reality actually instead of directly solving this, because you cannot directly solve this, you need to gradually improve it so elbow becomes the actual technique. Okay. But overall, whenever you have something like this, you can always say that if I don't know how to calculate this, I know this is larger than some value that I can calculate. And I focus on that value to improve that. Okay, sure. All right, so actually, what we're going to do, so we're going to this. All right, we're going to now go over basically the architect that's being used in diffusion in general, and then different types of diffusions. So let's just start with here. So in practice, in industry actually, the main neural network architect that we are using during the backward training to train for it is actually a unit. Okay, so unit is it has a flavor if you think about like an autoencoder, encoder, decoder itself. It's it basically breaks down the data and then basically expands it. So in unit, you start with a basically noisy image or image basically, and you go to pure noise. And during the reverse process, basically you want to reverse that. Now, well, in unit, basically, there are different versions of it. We will see. But here, what you are seeing is that the learning here will be that at the end of this, you get this. This is the model. Epsilon theta, and that means there's a model that predicts the epsilon for you. After training, this is your model. During the training, you need to embed time because as you saw everywhere, we have t, like a theta is a parameter of t. So if you think about theta is a parameter of t, how we can enforce that actually in learning, like if I'm training a neural network, I don't want to train 100 neural networks for 100 timestamps. I want to have one neural network. So but you need to account for time. So what would you do? During the training, you do basically time representation. So you basically embed the similar to concept of what you saw in transformers, when you basically add the time to the data when you go forward. So here you do the same thing. You have time representation that stands for where you at. That goes to a neural network fully connected. So you have a small neural network, couple of layers, one or two maybe hidden layers. Sorry, like a maybe activation ReLU, or depending on what you're using. that gives you one vector. You append that vector to the ZT that you have at that time step, and you pass it forward to the network. Okay, so that's the overall idea of unit, and that's how you basically work with the diffusions. Now, we have seen this over time. Ashkan, XT here and ZT are the same thing. Okay, so we show you that. So at a given time, the image comes from the first image with this boundless. Here, alpha with the bar is actually, so sorry for the consistency, but alpha with the bar is this 1 minus beta t. Alpha without bar is just first version of it. No multiplication. Okay, so now, okay, so as we have talked about that in the forward, as you add noise, basically this becomes worse and worse. Now we want to talk about this, what happens in this unit. So the layers are basically like this. So you have the encoder, which gets an image and basically goes down to some sort of like a latent representation, which is that Z, which is pure noise. And then you pick that which is your bottleneck also here, that latent, and you pass it to a decoder to basically expand it to go back to the image. Right? So that's the idea for unit for the training. Now there's something called a skip connection, which is really important in unit. A skip connection means that at any step, this is a good image for it. At any step during training, you actually concat the encoder with the decoder. So I start here and I pass to an encoder. The first slide, the first basic activation map that you see, Z1. And this is already have time embedding. Okay. Then when I go to ZT minus 1, sorry, ZT minus 2, one before that, in order to go from ZT minus 2 in the reverse part back to ZT minus 1, I give to the model what was the version in the encoder. So you concat that in order to move forward. So in unit, that's the main practice. You need to have this skip connection. You always concat the corresponding basically encoder, learn, and the decoder in order to predict the next step. Okay, so that's the industry practice. You need to do that.
Is that the purpose of that?
You need to do it. Let's put it that way. No, I'm going to tell you. So the purpose is that you want the model to know exactly what was happening. So you pass to the model, hey, during the encoding, because one way is forward, the other one is backward. So during backward, I tell you that you're here, but during forward, when you got here, you had this much knowledge. When you concat those two knowledge, when I want to now go backward, I have some idea, okay, previously I was here, so I'm going to go this direction. I get a better understanding, all right? So unit is a generic, basically, a strategy that we use in diffusion, okay? And actually, I think unit was before the diffusion, is a type of model that used in diffusion. So it wasn't developed for the diffusion. So, yeah.
So in the unit architecture, even the front ones, like the leftmost ones, the parameters are learned, right?
Sorry, let me just get rid of this. Say again.
So as we know, we have a concept of forward and backward, and the learning happens only in the backward for a diffusion process. So even here, the leftmost part, is the learning happening there, or are the parameters learned there, like in the transformation from one layer to different layers in the leftmost part?
Okay, I think it all depends how you train it. You can train them all together in one network, which is most of the time. You basically train it as one network. It's an easier architect, but the process is still the same thing, just noising and denoising. Yeah. This is an architect you choose to make the fusion, not the process of the fusion. The type of neural network that you use, you use it, train it all together. So,
Can you please unit again?
what's that?
Can you please explain unit again?
Unit is an architect, neural network architect developed by I don't know who's, I think it's some group, if I'm not wrong, if it's Stanford, if I'm not wrong. But it's technically some sort of like autoencoder, right? Encoder, decoder, basically. And during the in the diffusion, which our goal is that to keep adding noise, right? Yeah, we need an architecture. You need a model type for this. You want a model to learn, right? That especially this model is the technically, if you think about it, this model is the model back, right? Like from there to here. Thinking that's the main goal. So you need that F theta that we just talked about. You need a model. The model that we use in practice is a unit model. It's an architect that you use basically. It looks like this. It has a basically like encoder flavor, a bottleneck, a decoder flavor. What you are saying that in unit, there are a series of things that you need to do in order to make it practically work. One of them is that basically, except for this one in the center, you see there's a gap. Every other two, you need to concat them in order to go to the next step, to have some knowledge from encoding time. You just architect, you just basically add the data and just pass it forward. And during training, your goal will be that to repeat this back and forth somehow, that you can go from here to here, backward to the image. You should be able to do this process.
We concatenate what with what?
You see these blocks? This block to this block.
So those blocks are the matrices, right?
Just concat them.
At time step, for example, 50, we concatenate
with. So at time step 50 in the decoder, you concatenate it with time step 50 in the encoder. All right. So it's like you remember encoder, decoder, you have two separate models, encoder, decoder. Just be sure that they have same time steps, same architect, technically not time step here, it's like a layers. Every two corresponding layers, concat the result of them before you move forward. Yes? Yes.
How do you add time embedding to different layers? Because time embedding ideally would have one dimension, but
No,
all
time
the
embedding, why has a one dimension?
I mean, it has a
How do
fixed.
you add time embedding in transformers?
So it has a fixed dimension. So, but these layers have different dimension. Each layer is of different
You're
dimension.
concatenating to it.
Yeah, but still, like you should have something. For example, 4x4 you can add to 4x4.
So this is a model that also is time-based, right? So it's MLP model. So basically, we have an image on it. You produce a vector, and you just add that vector at the bottom of what you have. Just bear with me. I'm going to give you an image to make that simple for you. We go back, we just past that. First, same time representation as the transformer that you have seen is being used here. So it's kind of like you do time embedding across time. D is the dimension of the whatever data that you have. So I'm not going to go over that. You pass that to a fully connected, and it convert it to basically some vector representation that you pass it to the unit. Okay, we have an image for what you're asking. Just give you a question for that. Now, all of this, okay, this was just telling you that if you want to develop a diffusion, you need to use unit, okay? Now, let's go back to what we were talking in the previous part of the class. Well, we were adding noise over time, okay? Then the idea was that, okay, if you just keep adding noise, we noticed that when we add noise, the quality of images, like the more noise you add, the quality of image becomes better, actually. So that's the idea brought to come like an infinite level noise. What if we add as much as possible infinite noise to the data and denoise that? What will happen there? Why this makes sense? When you do denoising, when you go from pure noise to image, we say that if you take small steps, you produce a better result because you get a better guidance. So the idea of infinite level noise is that you basically end up with a really smaller, basically, steps to generate the data. So you have much better control over data generation if you do infinite noise versus if you have a limited number of noise. Is that clear? So now, what you see in the image below That's an idea of infinite, basically, noise. So you have an image, like a distribution, not an image. There's two modalities. Let's say that means one time your sample is a dog, one time is a cat. Two modalities. And every time, as you go, you basically keep adding noise and sample until you basically, it doesn't matter if it's from cat or dog. You need to go to a simple Gaussian distribution on the right side of the image. That is the forward process. But in infinite noise, basically, this is all possible amount of noise that you can add. So look at this image, and this is an idea of noise. So you basically keep adding noise to this. And those trajectories to show you that you can go different paths, different trajectories, basically. It doesn't matter where you go, how you cross. At the end, you go toward the same area because you want it to become a Gaussian, simple Gaussian distribution. Right? So that's the idea of like an infinite amount of noise.
Is it an actual graph or is it just like some simulation? So like is that
It's actual graph. I mean, you can draw this yourself, right? If I have an image and write a loop on your machine, we have an image, like let's say one image, like right? So one image, that means you have only one distribution. If you use two images, you get two distributions, two separate, one car, one plane. Write a loop. In this loop, using the equation that you have for ZT, put it on a loop of like 10,000 steps, for example. Keep adding noise and store the value of the noisy version. Store them somewhere. When you are done, plot it. You will get this, correct? The yellow. You should get that. If you have all the points of the noise at every time stamp, you get this yellow. Now I bring a new image. I have this plot, the yellow part already. I bring a new image and I see where does it go through it. That's what is real. All right, so this basically introduce a better quality images, this idea, and we're going to see that why. But one of the benefit that this infinite basic amount of noise is that it allows you to find exact log likelihood, which the previous version doesn't. So you can exactly know the actual likelihood because it's infinite possible. You go so small, you will find what's the exact likelihood. Similar to what we saw in autoregressive, it's exact likelihood. Diffusion with infinite noise is exact likelihood. Right? Now, this idea is called, this becomes somehow a stochastic process. Now, we don't go, also, the third one says controllable generation for inverse problem. We will talk about that. But inverse problem means that if I bring an image and I cut a center part, and I tell you that regenerate the center part, that's an inverse problem. We will talk about that later. We have it. Okay, so it allows you to control and basically to regenerate the missing part of the image. So this basically is a stochastic process, and that's why we are basically going to use the technique of the stochastic differential equation, SDE. Now, SDE is basically a general form of SDE is something like this. Okay, the function d times dt plus another function, like this is not a function, gt times dw. Okay, that's a stochastic differential equation. Now, the dxt is basically, so this is, again, this is assuming that infinite noise here. Okay, so dxt denotes the infinite small change in x during certain time. Okay, how much infinite small change, how much change in infinity you will get for x at this time step. Then you have fxt, fx and t, that's a drift coefficient, is a deterministic term. You have gt, which is basically the diffusion coefficient, and you have dw, that's called Brownian motion, okay? And that basically is kind of indicating of white noise, like how much, like infinite, like a white noise. So why SD all of a sudden? Why a stochastic differential equation? Because doesn't matter which types of diffusion you are solving for, all diffusions have a flavor of SDE. if you think about them, in diffusion, basically you have ZT equal some deterministic term, some noise, another term. That's exactly that equation, right? So all of the diffusion, they have this flavor of a stochastic differential equation. Okay, that's why we use it. We go toward SDE in order to basically solve the problem. But what does SDE tells you? It tells you that if you're looking at a random variable, okay, or like a particle, over time, how this will change. Basically, that's how what SDE tells you. So it's similar again to has same flavor for us in diffusion, which wants to see that an image how it will change over time. So now when we go to basically SD, so so anytime you see in diffusion SD, this is the version. We will see this second version, but basically what it has. So here what you see is two equation as kind of like a two types of diffusion. So we're going to talk about this, but in general, what the image that you saw was infinite noise. It's solved via SD. So this is the general form of the SD, deterministic term, infinite small noise, and GT is technically square root of 1 minus beta, which is this what was called the diffusion coefficient, basically. So now, if we will talk about the first term on top. This is called variance preserving diffusion. The one on the bottom, it says W log toy SD. So there is a version of the basically we have those slides coming up. There is a version of diffusion called variance exploding. Okay, so VP SD or VP diffusion versus VE diffusion. So anytime you see VP, the terminology, the equation is exactly what you have seen before. Because you have a deterministic part, you have a stochastic. You have variance and mean. Anytime you hear the term variance explosion or explosive diffusion, you only have noise. So in version of variance VE, you don't have that deterministic term anymore. At every time step, I just add noise to the image. I don't care about what was before. You just explode the noise, like the noise scale, as much as possible toward infinite. If you hear variance exploding, that means you don't care about that deterministic part, which is this. You don't have it in the equation. So you don't have that. You just have pure noise and that Brownian motion. You just keep adding noise. So you just until you go to infinite possible. So
in that scenario, could you write that same equation, Professor, for the second part?
It's written under it. DXT is...
No, not that. I understand that terminology. I wanted to relate with this.
Just add noise. So this is called DXT. What amount of change you add to the image? Purely random. Add noise.
There is no image.
DXT. XT plus DXT. That becomes the next time step. DXT means the change in the image. How much change you will have in it comes from this, right? So you determine the change and you add. In variance explosive, you don't have that knowledge from past, the deterministic term. You're just adding noise. You keep add noise, it basically explodes. We're going to see some images on it. So
Is that DZT or DXT?
D.
It should be DZT, right? Because every.
Okay, you guys need to understand. You could see an X, you could see a Z. It's a variable. Okay, I couldn't change the image, so it's in your head. Just take as a ZT. Yeah. Anytime it's confusion, assume the image to be X0, and anything after is X. That's the same as Z. I couldn't change the image because the image is copied, so just that's the same thing, correct? All right. So again, this is just to summarize, but here, when you want to connect the diffusion to ST, this is the equation, the first term fxt, which comes for that deterministic part, is calculated using this equation. 1 minus basically half times beta t. Beta was that, remember that basically the scheduling coefficient factor, times x. That becomes this fxt, which is the deterministic change. It's kind of like it has the same flavor of what do you call kernel trick. For at any time stamp given x, because I know all the possible schedules of beta, I can tell you what is this value for that time stamp. Then you have this dt, and then with respect to t, and then you have this gt. Gt also being calculated using this equation, a square root of that beta. And beta itself, there are different ways you can define it. Okay, so it's author choice. There's a version of beta, it could be this. At any time stamp, you have a minimum beta and maximum, maybe 0 and 1 or something else. At any time stamp, you can calculate beta using this equation if you want it to be linear. So you can decide if you want to increase beta linearly or if you want to have some nonlinear function. So that's just one example of how you define that beta.
What are the difference between the results of this variance explosion and variance deterministic?
Wait, we'll get there. We're just talking about it. Let's see the equations, let's see everything, and then we get to the results. Okay, we have the image of the results. All right. So now, in general, when we are coming to this basically SDE types of model, there are a couple of versions that you might see out there. One is variance preserving, one is variance exploding, discrete noise scale, and hand design SD, right? And there are probably more like the research papers coming out. Now, this is variance preserving. In variance preserving, you have the deterministic drift, you have a stochastic noise, and the variance. Basically what this does, as I say, it shrinks the image to a small noise. Right? It technically shrinks. Why variance preserving? Because it doesn't change the variance over time. Because basically it preserves it. However, if you go to variance basically explosion, variance SD, this becomes the term. You're just adding noise, so you're not preserving anything from past. You just keep adding noise to it. Noise grows over time until it goes to basically infinite. Then, if you go to discrete noise scale, this is where it becomes really similar to what you saw in score-based models. When you had discrete level of noise, basically, it's really similar to that. What you will see here, and we're going to talk about it, is a technique called Euler-Maruyama, which is a common technique in diffusion for discretizing. So if you do infinite amount of noise, which we know it gives a better result, during generation and something like that, well, we cannot do infinite. So what we do, we discretize basically the path, the trajectory, under a certain level of like bandwidth, like bins. The technique that we're going to see is this one, Euler basically technique. This help us to discretize the process. The next one is like a hand design, is just an example, like the papers out there. You will see that this is totally hand designed. So there are a series of properties that you need to keep in mind, but you can basically define your own version. Okay. So as long as it's ST, is a stochastic basically. Now, so let's just start with so this is the version of variance exploding. So there are two pieces, forward and backward. So during the forward, this is the dxt. dxt means amount of change you need to add to previous x at that time. Comes from just total noise. Okay. In the reverse process, when you want to basically reverse that, how much you added, that comes from this equation. Okay. And this equation has two main pieces. There's this that sigma, which is stands for that, there's like the variance that you have. It's like the noise level basically. Then you have this score function, which you saw before, which what does the score function do is guide you toward the dense area in the image space that you have. If you had all possible, if you had like this is a total space that you could be on, and we have seen there are regions of this space that you had data from that, dog, cat, birds, that the score function guides you toward the one that's closer to you, right? It's because it's a division with respect to data, not with respect to parameters. Then you have this second term, which was again infinite small noise. So in reverse, basically, you use this equation. In forward, you use this equation. Yes.
So the second equation, are we going to go through the derivation of how we got that equation, or is it a standard equation? Reverse SD, it's a standard thing?
I don't think we will go through it. Maybe you have it in your slide, but I think the best practice for you is that to try it. But that's a standard right now. Okay, because if you're using the well, you can drive that actually, but I don't think we are going to go through that. So this basically the reverse goes to that, and we will see for the next one also we are not going to drive it. That becomes another class for diffusion if we want to do that. So in the forward, basically what happens here, you could just keep adding noise until you get to the pure noise. In the backward, you use this function to basically do that. The important part you want to remember is that because this went toward this score-based model, now the guidance over making the image better quality comes from a score function, right? So you see that there's a change in the flavor of what we are doing. We are not predicting noise right now directly. So we are using the density that we like this, like a likelihood. This density function basically tells us that which direction, like again, if you think about it, if you close your eye and you want to go uphill, even if you don't know, if you take a step, because you know it's uphill, you can feel it, you can't go that direction, even without knowing where is uphill, right? So that's what the score function gives you. It just gives you a direction toward the basically a steepest hill. So now, so this is going to be a reverse process. I'm going to just open that. This is also real. So you start from pure noise, you sample from this Gaussian somewhere, and you let the basically data go through. And because this is coming from two modalities, in general, it needs to go to one of those two, basically. And as it goes, basically, it goes back to the image. And this is from pure noise. You know, it's not that noise doesn't have any knowledge about the actual image. The model knows I'm here randomly. The closest one to me is this, and by random, that closest one was that image of a bedroom. So now, when we go to variance preserving, the equation is changing because during forward, now you have two pieces. You have the deterministic and the stochastic. In the variance explosion, you didn't have that term. Now you have both terms. Now, during the reverse, that delta change comes from this equation. In other words, fxt minus g, score function, g times dw, the Brownian motion. Okay. Now, so this becomes during the backward, and again, iteratively, basically, you reduce that value, you update your x, keep going backward. And we will see the equations for, so you saw already the equation for fx. It's technically -1/2 beta t times x, fxt. And gt was a square root of beta at time t. So anytime you see beta g, so let's call it gt, this is this. And anytime you see xt, this is technically -1/2 beta t times x. So if you see gt to the power of 2, get rid of the square root. Okay, so that's basically what you have over there. So now, what happens here is that which I hope by now you know that anytime we are calculating this, basically a score, this vector field of the gradients, we already know that from a score-based model, we can estimate that. So here, the training, the objective function goes toward a score estimation. So we focus on training a model that can predict this. Same thing as score-based models. We also in score-based model develop a model that can predict that. So we are going to do the same thing. In the fusion, in this version, we're just going to focus on developing a model that can predict the score. And again, what does the score tell me? That if I'm closing my eye and I'm going up, tells me, okay, keep going, turn right, turn left. That's exactly what it tells you. So now the training objective becomes the just basically some expected value, the actual basically gradient score field, and the score, because this become totally a score-based training. Because the only thing we are doing is to train a neural network that can predict this. And during the training, you have this, because you have the data. If I can learn that model, then during the inference, I don't need an image. I just start from noise, and this will guide me where to go on this map. Okay? So this is, again, all of this is same thing that you saw in the score-based modeling. It's kind of exact the same, exact idea is being applied here. Question?
Training, do we have that?
You have, always you have that. If you have data, why you don't have that?
We don't have PLs.
This one? Well, if you put all your basically data here, so what does Px tell you? This is gradient of log P of x. What does that, so there's one scenario here. So during the score modeling, one thing we saw that if we don't have P of x, which was this log P of x, if we didn't have it, what did we do? We did change of variable, and we again went to some sort of like a noise prediction. We added noise to the image, remember? So this x becomes x plus some noise. Now, because it's x plus some noise, I can calculate this. For actual image, I couldn't, but x plus some noise I can, because I know the noise. I learned the noise, right? So this becomes same thing that we saw in that class. Okay? So I'm not gonna go over it, but it's the same idea. You need to do some tricks if you don't know this exactly. You approximate, right? That's the idea. I want to learn that they approximate this. But yes, you can do that. It was expensive. If any of you remember, there was two terms in that equation, Jacobian and a Hessian. And I say that the Hessian was so expensive, that's why the score-based model went to the second version of the score-based model, which became more of like a denoising concept. Then it didn't have that terminology. But anyway, we passed from that, is in your slide. So now during the reverse, the d of x comes from this equation. Right? So again, this terminology. So instead of f now, basically we have this. So we're basically using this s theta. We approximate whatever it is that which tells us how much change I need to do. Again, this is doing denoising. I'm going backward. What it tells me, you need to take a step in this direction. This exactly tells you where direction to go. You scale it. And this is going to be that stochastic part of it, the second term. So you have some deterministic part and you have a stochastic part because you still want some randomness in it. So now this comes back to this idea that we just talked about, the Euler-Mariouma technique. So in reality, if you want to solve for SDE, which is kind of like infinite small amount of noise, well, it's not that easy to calculate that. So you need some numerical solver for it, a technique that actually can analytically solve it. So the Euler-Mariouma is one of those techniques. What it does, it rewrites the equation in this form. Okay, so x at a given time plus some change. So at this time, I want to go here. So that's xt plus the delta theta is where I'm going. Comes from where I am, some drift term, times how much is the time gap between these two time stamps. So delta theta is the time gap, plus the diffusion value, times the square root of the time gap, times z. The previous basically noise, or just noise, sorry, actually. It's just z is total noise here. Now, Z is a sample from Gaussian here. Now, so doing forward, this is for variance explosive version, which we during forward. Remember, in variance explosion or explosive version, you only have noise that you add to the previous image. So the second term is the only thing you have. Previous image plus I add some noise. Previous image plus I add some noise, and I'm repeating this. During the reverse, this is the same equation that you saw before. The only difference that you see is this delta t that has been added, okay, which stands for discretizing time. We're going to talk about it further. So delta t here helps you with, so this, basically this is not absolute value, it's modular. Like what's the size of delta t? Like how many bins you have? That's what it means. And delta t itself is just a time gap at that moment. So this invariance preserving version, same idea. You just basically add this delta t here, and you have a delta t here. You have a delta t here, you have delta. So the same equation that you saw in a stochastic version, you're just going to add a delta t over it, right? And what is delta t? We keep saying, this is delta t. Delta t is equal t over n. If you have 1,000 steps that you wanted to take, and you're like, wow, that's too much, I cannot afford it. But you select an n, which is as a step size. You break that 1,000 steps into a smaller windows, buckets. So that's where the delta t comes from. Now, in practice, what is more common that you see in industry, n is basically set onto 1,000. So most of the time when you see images being generated, they're actually 1,000 steps. Kind of, if it's analytically basically approximated, it's going to be 1,000 steps. So, and again, that's companies different. Maybe some companies do something else. But what it means is that if this is an infinite interval, like you cannot do it, like it's infinite, just imagination. So let's assume 10,000, 100,000 steps you wanted to go. Just break it down into thousands. And this becomes every bin. From T0 to T1, delta T is a bin size. Then another delta T is a bin size. So it's going to be equal bin size, basically, right? So you use that to take a step. One thing that it has been proven in practice is that if you select n, so if you select n, the denominator, to be large, delta T becomes smaller. If delta T is smaller, you get much higher accuracy generated images, but much higher cost also. Because why? Because you take much smaller steps, you need it, the computation cost goes up. If n is small, delta T becomes large, your image quality goes down. That's when you rush through generation. So you need to basically have a control on that value. So again, this technique is only like a technique for analytically solving a ST, because otherwise it's kind of like a challenging. Any question on that? What's going on?
Too much done.
All right, so this is just an example. This is for variation explosion explosive version. Just to show you that in 2 times step how the operation will go through. Just going to pass that. And this is, I put another example for variance preserving version. Just so you get some sense of what will happen. Same equation, you just introduce a delta T, update, another delta T, update. All right, so in summary, for this idea is that you start with a pure noise, and every time step you calculate using S theta, your model, the guidance over which direction to go. You apply that, then you do a sample basically from the Z, putting it in the equation that you saw above. You're assuming that because you're using a Euler approach, so you have some delta T in mind, and then you reach to the end. At the end, you have some image. So it's kind of like an approximation version of that. Now, before, this Euler technique is being used. It doesn't have, it has its own pros and cons, but it's a really active technique that's being used in industry because it helps you actually approximate and analytically be able to solve it. Otherwise, it becomes more expensive. Now, we're going to talk about another version of diffusion that you might see out there. It's called predictor-corrector version. So in the idea of predictor-corrector version in diffusion is that we technically have two steps to solve the model. In order to denoise, to go from noise to the image, you have two steps. This makes the process faster. So the idea was that how could we make it faster? So instead of we be really careful in taking steps, we have a model that tells me, I have a good hunch that you need to go that direction. So it tells me this is the next image. Then we have another model like a discriminator comes and say that you are off by this much. You're here, it's correct direction, but go up this much. So that becomes predictor corrector. So predictor helps you over the direction where you need to go. Corrector puts you in the correct spot that you need to be. So this takes you here, this brings you here, this brings you here, this brings you here. So predictor corrector makes the process faster. Because now you don't need to worry about taking so many smaller steps. You can have two separate models. One takes the direction, the other one corrects it, basically. Does that make sense?
Why is the corrector pointing towards the exact midpoint of the two distributions at the end?
Is it like that's not the corrector? Corrector is a red line.
Oh, sorry.
That's
sorry, direction predictor, basically. Yeah.
Oh, it's a predictor. It just predicted. Then a corrector will correct it. So it's not you don't see it. This corrector says go from predicted corrector from here, put you here. Because on the last one, just you have a step, then corrector fix it. So I thought this diffusion was a chapter that everyone was like, oh, we want to learn diffusion. All right, so this basically the idea is kind of like this. So you have this equation, same step, same thing you can do. You basically use the Euler technique to kind of discretize the time. These are the type of thing that you need to do in practice. If you want to train a diffusion, you need to have practical way of solving it. Euler method is one of them, predictor connector is one of them. Otherwise, you just end up with infinite loop and you don't generate anything. So these are the practical way of training it for you. So now the corrector, so the predictor, they have actually two different approach to solve the problem. The predictor is just technically using the SDE. And SDE is just kind of like a based on the gradient of the thing. So kind of have some idea of like you need to go this direction. It knows the direction basically. But the corrector is actually a score-based MCMC. Right? If you remember MCMC, once you call a Markov chain, right? So it basically helps you to correct the path. So this too is important. The steps are different types of algorithm, right? So it's kind of like you solve them differently. Okay, so that's the equation for the update. So previous timestamp plus some epsilon, that means like some step size, like a learning rate, times the gradient of the vector field, the direction that you get on the vector field, plus some noise. If you remember in MCMC or Langevin dynamic, when you sample, you add some noise to it to ensure that the second part is just a pure adding some random noise, so in order to be sure that it generalizes. The first term comes from deterministic previous timestamp plus the information that you get on a score field. Okay, and the third one again is just pure noise. So, and again, this is just to summarize the predictor corrector. Predictor using basically ST dynamic. Corrector use a score-based MCMC. And it improves the sample quality. It helps with the speeding up the model because you don't need to be really careful about where you go on every steps. You have another model that helps you. And it's one of those techniques that you can basically apply. Now, this example of the model, the images that are generated by predictor corrector. So the qualities are pretty high, right? So now, the next technique, this is the one that's kind of like despite the fact it's going to be costly, yes.
So, like, how does it look in the architecture of neural networks, the predictor corrector? So unit, like where do we introduce the predictor or the corrector? In the
So,
architecture?
so imagine you have a unit, and maybe you use again this architects of your choice at the end. But you have two models. One model tells you that like how much noise you need to basically deduct, right? And that model doesn't need to be really good.
So we train all together everything.
The model that needs to be really good is the second one, the corrector, right? So the predictor is just kind of need to know which direction to go, right? It's kind of, I have a good example. Think about it, you're trying to make an art. You have one artist that is good only at doing a sketch, right? So the predictor is just a sketch artist. The corrector gets that sketch and colors it, paints it. So that's the way that you can look at it. There's like two different models. You train them together. Architect's choice probably similar to unit, but it's like also at the end the engineer basically design. But it's like you train them together. All right. So now this is where the problem becomes like much more interesting. There is a version of diffusion that's deterministic. That means you can go purely back on one line without any stochasticness in it. And that's called ODE. Okay, so ODE, ordinary differential basically equation, is a way. So you saw SDE version, which is a stochastic differential equation. Then you have this ODE, ordinal differential equation. The idea of, so what you see in these trajectories, the red is a stochastic. The yellow, the white is OD, is always fixed, one direction, right? Similar, now this kind of gets the flavor of what? Which model we saw was deterministic? Gives you exact from noise back to image, image to noise?
Flow models. Flow models.
Flow models, right? So that becomes exactly same flavor, not exactly same thing, same flavor. Now, the idea here is that so in SD, this is a version of the variance explosion. If this was the SD, the ODE version basically becomes like this. Okay, so dx over dt is the same thing as dxt, right? Just keep that in mind. So what we will basically see is that, so the idea here is that there's a version that way we can basically have deterministic answers. You always know exactly what you're going to predict, you're going to generate. Now, so for this is a SD. For any SD like that, basically you can get the ODE version basically like this. So one thing that you want to know is ODE doesn't have a stochasticness. So the second term doesn't exist. The second term was where you add noise, right? That doesn't exist in ODE. So ODE is only with respect to fx. So technically, that formula is like this. So dx is fxt dt. That's a version of ODE. When you see dt here, this has gone the other side. Okay. So that becomes ODE version is purely deterministic because you remove that stochastic version from there. Same equation, you just remove the stochastic node. Now, so this is a formula for the version which was the variance preserving. So you've had this, and you get this. This is the ODE form of that. Just remove that stochasticness. Then you have, so if you look at this idea of like an ODE, during the forward process, we add noise. We don't want the noise to be stochastic, deterministic. Okay, so this part that you understand. During the forward, I add noise because you want the model learn to denoise it. So when you train this using ODE, the forward process is always stochastic. You just add enough noise to become pure noise. Noise is random, right? So forward is SD. During the reverse, you do OD, which is purely deterministic. So for forward, just use whatever you have seen before. This is the original version. This is discretized using Euler method. For backward, this becomes the backward version. This has become discretized of the same backward. So you remove the stochasticness in the backward process because you're using OD. Okay. So the reason I don't say much on this, because the only difference is that we removed one term from this equation, which was that the random noise added. We just remove that and that becomes the ODE part. So now I'm not going to spend too much time on the idea, but the ODE has exact likelihood calculation because it makes sense. If there's only one pass that you can go, you can find the exact likelihood. So it basically gives you exact likelihood. It makes it really, again, like some sort of like autoregressive models that you basically can predict the likelihood, right? So it gives you exact likelihood because you have all the steps. It's just one direction. Now, I'm not going to spend much time on it, but I just want to give an idea of like this is a proof of why it's exact likelihood. There's a I don't know, like there's a theorem, basically, you can maybe call it this way, continuity equation. And continuity equation says that this gradient with respect to t times divergence times probability of t times this term, dx over dt, equal to 0. This is called continuity equation. So the term dx over dt is called velocity. Right? This is when you think about it. The easiest way you can imagine this is think of a river. Right? A river goes in a direction. At certain point, the river is wide. At certain point, the river is small. The flow goes through this river. At certain point, it is wider, is slower. Certain point that is wider is basically faster. Right? Now, if you put a leaf on the river and see the flow, how this leaf is moving, that's the idea we're going to basically use. So there's this velocity, which is the direction and speed at different times. It's not the same based on where you are in the space. That space and velocity is going to be different. Then there's this px times dxt. That's probably current. Like it's the current, the amount of water that goes itself is either this like a really wide river or just really narrow river. Okay. Now, dx over dt is the same equation that we saw before here. That's the same equation. Dx over dt, you see? So that's the equation. So now, one thing you can basically look at is that if, so these are the terms that you saw before. fxt was the drift from the ST, gt was the diffusion scale, and this is the score function. So intuition, if you have a probability of x is 0.8, okay, and this term, because you in the previous slide, you multiply this by that. If this term is -1, so if this term dx over dt is -1, that means the flow is going to the left in the reverse direction. If it's positive, means flows to the right, right? So it has a value. You multiply by this, it tells you, so if this is -1 and the probability is high, it tells you large amount of basically a large amount of basic probability or image is moving to the left. If this is a small, probability is small, it tells you small amount of energy moving. So you can think of a Gaussian. When you are in this region, you have a high amount of data, P of x. P of x is high. So you go either left or you go either right. When you go to the right, depending on what's the speed of going and what's the basic velocity. So which is that term. So dx over dt, it tells you that velocity and speed, what speed you are actually denoising, changing the data. That will guide you to this direction. Now, if you're here, the probability is low. The second example, P of x is super low. Now, if you go this direction, it guides you toward high probability. But by how much, you need to determine that based on your velocity and the speed. And that's the d of x over dt. Okay, so this idea basically tells you that how did we're moving along this distribution space to go to high basically probability or get away from high probability, like adding noise. So, now there's a term over there that you saw is divergence. And that delta X, we're going to talk about it quickly. If this is positive, that means mass leaving, density basically decreasing. Mass leaving means you go to the right. You're going from mass to small. If it's if it's negative, mass arriving, that means you are coming from low region to a dense region. If it's zero, that means you are basically staying the same. So that's the definition. Now, and the example with this is like expanding or basically shrinking a balloon. You can think about it. Yes.
Professor, we spent one class and we understood that, there's no way of going back directly. A decoding process has to be done slowly, step by step, approximation, take small steps.
But this is telling you it's possible.
Exactly, right? So how did this happen? How did people just come up like, okay, now you can just do it directly. Why did you do all of that?
All right, let's continue. It's like you're asking a question like how this algorithm comes off. Well, someone is smart singing over there, and then they come up with it.
Understand, like in very simple English, like the intuition behind what people.
So the intuition is that if there is a path forward, right? I know I can go from there to here, in all possible way, right? There should be a way that I could come back exactly. I'm going to go shopping. I could go take any road. Let's say there is one exact road that takes me. And the only way I can go there, if I take really small steps and every time make a check on my phone and see where I am and guide it.
Yeah.
That's the idea. It's more costly, we're going to talk about it soon.
Okay.
It has, of course, if it was the only solution, then it becomes the only solution. It has pros and cons, we will get there. But there is a way that you can guide yourself based on certain parameters to exactly go like one direction to the answer. But like every other algorithms that you have seen, like in diffusions on different versions, they all have pros and cons. That's why we keep seeing different versions of this. Bear with me, we get there. So, and I'm not going to prove this, but all of that basically tells you that this term is equal to this term. That means this proves that you will get exact likelihood. Okay, that's the proof of that. Now, this becomes the exact likelihood term calculation. Probability of X will be calculated this way. We don't want to go over it, but it's like solving it. I'm going to just talk about this gradient and divergence. When you heard the term divergence, there's a difference between gradient and divergence. Gradient is whenever you pass a scalar and you take a derivation with respect to a function. That becomes the gradient. Divergence is when you take the derivation from basically with respect to a score field and gives you a scalar. So the term between gradient and divergence, one of them gives you vector, one of them gives you a scalar. Okay, so gradient, what does it tell you? Direction of movement, right? Direction of change. Or basically direction of change and basically how much change. The divergence on the other end tells you that how much things is moving. So one, it tells you that what direction to go. The other one tells you that how much is moving. The mass basically is moving. Okay, like how is it become larger or becomes smaller basically? All right, so now in summary, ODE and SD, well, it's going to be that answer to your question that why this versus the other one. Well, OD basically is kind of like it simulates some noisy forward, similar to SD, but the backward is totally deterministic. SD in both direction is noisy. The steps basically in this one you take basically less steps in the basically OD in basically depending on how you look at it, but sampling becomes more difficult. The robustness is not that robust. It has its own issues, and it's kind of like it has certain applications only, depending on what you are trying to do. So SD is still more favorable because it's pretty robust. Why? Why? Think about why robustness. If I have a deterministic decision always, I might overfit, right? In SD, you keep adding noise, so your model is trained with more noise and stuff like that. So it's more generalizable, so it has better robustness, you know, to basically to randomness. In basically OD, you don't have that, so it's not that robust. All right, so now we want to talk about, now we're going to go over different types of things, like applications of diffusion and how you can actually, in practice, apply this to different types of image generations. But first, we want to talk about one thing called inverse problem. So in, especially in basically image generation or stuff like that in basically the vision, the idea is that if I have a partial image, how could I extract the original image from that? It's either, like, for example, colorization. If I give you a black and white image, can you give me exactly back the original image? If I give you an image and I cut a spot in it, could you reconstruct it, right? So these are the idea of like inverse problem. Now, the inverse problem says that an image, or basically an y, comes from a function over the basically x plus noise. So y is the noisy version, like the corrupted version of an image. X is the actual image. You pass an x to a function a. A could be anything, like a function that cuts a corner of the image. It could be a, right? So, and then you add some noise to it. And you basically have a noisy version of it. Now the idea is that could you recover x from that y now? So that's the idea inverse problem. You corrupt an image, like a cut corner of it, remove colors, flip it, or do something to it, basically, so can you fix it? Now, the framework that will be used is pretty straightforward. It's Bayesian. Bayesian says that probability of the real image given the corrupted version comes from this times that. The likelihood times the prior. The prior comes from, so the prior P of y given x is technically a Gaussian. So prior of y given x is come from a Gaussian with mean ax, and if I'm not wrong, is sigma to I. Depending on what we are using, I think it might be just I. I might have the, yeah, that's correct. Sigma to I. Some sigma. So that's the likelihood term, and that's basically the prior term. Now, in basically think about this. So in a standard diffusion problem, the change at every time step, how much change in x you want to have, delta x, right? Basically, you have this equation, right? And you use this using maybe ODE to deterministic solve it, or ST, you know, a stochastic solve. In inverse problem, you add one additional information here. But first, let's understand this term. So if you are looking at delta x, what do you see here? There is a deterministic term, f, minus this term. GT is also known as basically beta t here. If this is GT to the power of to get rid of the square root, right? What is the second term, the last term? A score field, correct? What does a score field do? It guides you toward the region, again, I wrote this so many times, the region with which is closer to you, and it has a higher probability of arriving, right? Now, what if I want to guide the model to go to this region? Class conditional. I want to generate the image of a dog. This is a cat. The closest is the cat. How can I do that? And that's where the additional version of diffusion, which we are going to see, that's the idea will come. So you can guide the model by adding a second score field, gradient score field. This one to the one that you already have. So you have another distribution, which is the conditional distribution of corrupted images given the original image, right? And then you take basically this derivation of that with respect to x, that also give a direction. So if right now, let's say your normal score field tells you go this direction, the second term in the parenthesis, the last term, tells you no, go this term. You add those two together, you end up going here. And then another step, maybe this one says it's still here, but the other one says no, go here, and you go here, and then slowly it will pull you toward this one. That's because that's where the conditional concept steps in, because now you can generate image using prompts. We're going to see that. And basically, all you need to do is that the score field, add the conditional basic concept there, conditional score field. Clear? All right. So now, what is A? Again, A is just some function that transforms your image. Could be a Fourier transfer, mask pixel downsampling, or anything. Basically, could be an A, function A that you are using. Okay, so it's nothing important. But so these are just examples of function A that you can use: masking, downsampling, linear projection, partial Fourier identity. And there's way more, and all has different basically reason for using. But all you want to know is that doesn't matter what function I used. Unless they haven't totally got rid of the whole image, then there is a version that you can basically fix it. You can basically fix those missing pixels, or basically fix the image, color the image, and so on. Now, this is an example of you can exactly order the model to just every time that you sample, it should be a bird. Every time you sample, it should be a deer. By doing so, you tell to the model only, because it's otherwise it would have been random. Every time you just either get bird or you get basically deer. Now, in order to change your diffusion model to be conditional on imaged class that you want to generate, okay, that becomes class conditional generation. Let's say there are k classes that you want to train your model to generate from. K possible categories. Then what you want to do is that you want to somehow incorporate that in guiding your model. Okay, so this is just a definition. All you need to do is, so let's say you want to go from here. All you need to do is that use the concept of Bayesian, and the part which is the score function is previously without this concept of inversion and conditional, you only had this term. Now you add the other term to it, and you use that. So simply by doing that, you actually can train diffusion model to generate image with respect to the class that you are interested. That is, every time you sample, if you just tell me, give me a cat, it will generate a cat. It's not random. It will generate you a cat. So that's the same thing. Okay, so now there's another version, which just comes back what we talked in the other class. What if I have a classifier? So classifier is that there's a type of model that you basically type of diffusion that you have another model, another classification model that you pass the conditional to, and it basically predicts the class for you, because I didn't know it maybe. So think about it. If I didn't know what's the image, so you can pass it to a model, and the model makes a prediction for you. What you can do is that you can simply take a derivation of classifier in order to update the parameters of the diffusion model. I have a classifier, and it's supposed to generate a bird. And when I pass it to a classifier, the probability of bird as a softmax is really low. I do a back propagation to the classifier, gives me some update. I add that update to the updates of the diffusion, and I update the titles that they have. That becomes classification based. So now you have two is jointly trained. You have a classification model and you have a diffusion model. And you use the gradient from both to update the parameters. So this becomes something like this. Same idea. So you have this score field, and you have the derivation of basically log of the whatever you get from the classifier as a score function with respect to x. So concat those two, just sum those two, update the parameters, and continue. So all of these additional techniques that you're going to see, they all have similar story. The technique is STOD, one of these two. You just, all you need to do is that to guide the model, because we know STE a score-based function, basically, especially, it's to guide the model based on the higher density. Well, what if I could interject in this direction and say that, no, don't go, come this way. That's the flavor here. That's just what basically we're doing. So, all right, I'm going to just pass this one. Now, this is just an example. So if you have an image and you cut that corner of it, like as you see the part which is black, and you repeat the process, every time you see it will generate something else, but it will generate the image. All right, so there are differences, if you focus, there are differences in the surrounding, like the curtain or the chandelier or stuff like that. Now, the next thing is that image colorization. Just give you an idea, this is like quick. Imagine A is a function that you pass a colored image and it basically convert it to basically discolored, right? Gray scale. And you want to inverse that problem. So there is a function actually that you can use for basically converting an image to grayscale. This is what you do. If I pass an image, this does one step toward gray scale, and you need to repeat this process, and you will get to the basically gray image. Now we want to reverse that process, and this becomes the gradient of the condition gradient comes from this equation. Okay, this is the equation of the condition. I'm not going to go over it. You add that to the score field of the basically diffusion model and train it. And that over time, basically it's the same thing, over time will do something like that for you. You have image, you go to discolor, or you go from discoloration all the way to colorization. And these are, again, all same diffusion, you just add some additional direction toward the model basically updates. All right, so this is just an example of the same thing if you do classifier guide basically version. So during the ZT-1, you can use some knowledge from the classifier also to update the iteration over the image. So now the final part we're going to quickly go over those is like a different version of that you can accelerate or improve diffusion model. Well, first one is accelerator sampling. The idea here is that could we do a faster sampling techniques? You know, it's pretty slow, the diffusions, that's one of the challenges. And accelerator sampling says that instead of take these steps slowly, let's try to, similar to what you saw, discretize it and then take sample like faster. Well, it has its own pros and cons, like the quality of the image maybe, depending on what's the sampling interval you use, might be worse or might be similar, depending on, again, how much is that sample. The second one is a parallel ODE solving. Now, I'm going to play this link. So from a pure noise, it goes to a really basically high quality image. So this parallel sampling idea is if instead of just take one step, you define an interval in one go. And here, this is the interval. You see, I want to do a batch window of 4 steps. And you do this parallelly. And then you concatenate them together. It becomes that long trajectory. And then you look to see that how much you were off. It's kind of like it's improve the speed of the process. It's just a way of making the process faster. Then the other one is the distillation. Now, distillation is a way, probably it's like a way that you make a larger model distilled into a smaller model by transferring the knowledge to them. In diffusion, one thing you can do is that if you're saying that if I have a teacher that takes steps really slow to do something, I will train a student that for every 10 step, for example, that the teacher takes, it takes 1 step. And I compare the result of that 1 step of the student with the 10th step of the teacher. And I want the scale divergence between to be small. That's the distillation, right? So you keep doing this. So you train a much smaller model that also takes much less steps to predict the same quality, basically, image. Now, this is actually an example of distillation over these diffusion models for different noising steps. If you do 2 steps, that means for every 1 step of a teacher, 2 steps of a teacher, students take 1, 4, 8. The qualities never go down. They're really high quality images. They're much cheaper in compared to, of course, the larger model. And depending, the training part is important. You need to be sure that you can train them. Now, this brings us to the last part, and which becomes the state of art most these days of the diffusions. First, we're going to talk about latent diffusion models. Now, the idea of latent diffusion model was that image has high dimension. So going from image to image is like a really expensive and slow. Could we first pass an image to an autoencoder that gives us a latent vector and just do diffusion over this latent vector so you get an image, you pass it to an encoder and gives you latent variable, which it's not noise, it's just a latent like hidden features. Then you add noise to this to go to pure Gaussian, and your diffusion becomes to go from this back to here and have a decoder to generate the image again. Why is beneficial? Because I don't need to go over all possible, that high dimension over images in diffusion. I only get maybe 1 vector that I just need to add noise and denoise from that. Right? So now during the inference, all I need is just a vector of noise, pass it through this, and basically generate an image. So that becomes a basically latent version. You see there's a Kale divergence over there between as a cost function between the diffusion. Now, it's most of the time it's kind of like you pre-train that autoencoder separately. You don't want them to bundle together. That's it has its own pros and cons. But this is one of the interesting one that I saw. And what you see here is a diffusion model that can get conditioned on anything. Semantic mapping, text, representation, image. Basically, you can condition on anything. So the way that you see here is that there is a pixel space. This is the part that you have encoder, decoder. On top, image comes to an encoder. And that gives you this vector. Start adding noise to this vector. You go to a fully noise random vector. You pass that to here we want to do reverse, like same thing. When you want to go backward, now you have this model, which is job is like, think about it. If you have a text, you have a transformer, text transform, text embedder, gets the text, create a vector embedding. You bring that and do attention across this. And continue the process. And this will carry along the way. And it has also the time concept in it. It could be an image basically embedded. So you force the model in the backward process to add, basically to act with respect to the user's prompt. And the idea basically becomes similar to what you saw. The score field plus the guidance score field, the direction that this one provides you. And you keep doing this process until you get to ZT minus 1. 1 step to the end. And here you have one additional basically neural network, which is responsible for converting that to 1Z. And that Z goes to this decoder of your encoder, and it generates the image. So these are where you see diffusion models that are able to generate from any prompt that you talk with your ChatGPT. They say that build me something like this, that's could be an example. Okay, we don't know what goes behind theirs, but these are the type of diffusion model that you can now guide them to build things. This is we see an image after that. You can also do class conditional. That means during the forward, basically during training, you can actually add this class to every step appended to it. Just remember the class is this. Just remember the class is this. during the training. You keep doing that, and the diffusion model learns the guidance basically. So the benefit of this is you don't need a classifier. It becomes a kind of like a classifier-free version. On the other ones, you needed classifier. This one, you just add the class to the data. So this is another example I saw pretty interesting, and this answers your question. I told you we'll get to the part that you wanted. But so here, this actually what they do is kind of like anatomy based. So they have this image, it goes to a decoder, encoder, you make it total noise. And then you pick that noise, it goes to this unit, and you have this additional, so you have time, you have category, goes to another model, class, and as it goes, this what the part that you see here, it should be same dimension, basically. You ensure that it's concatenated, but exact dimension is kept. So you keep adding, and then here you have, and like in this paper, they actually did this really interesting type of thing. So you have anatomy condition, shape condition, class condition, all of those you can condition. And at here, they did repeat it a couple of times to ensure the quality is good, and you can basically generate the exact image. And that image that they generate is going to be anatomy based. Like you basically give a noise to the model and it says that this noise basically you're going to generate, I don't know, like a skull, right? So, and you define the shape of the skull that it should be also like that. And it's able to generate it for you. So, this is also this classify free version, which we just talked about. And this becomes another type of diffusion, which the idea is that we want to make it faster, but we want to make the quality better. So in this version is kind of like it has a cascading, kind of like hierarchical diffusion. So the idea is that instead of having one unit, I build series of units. But every unit architect is simply encoder, decoder. It's not about diffusion. But in every unit, I have a smaller, like I start from really a small unit, which gets a really small square noise and produce a small dog. Then I pick that small, basically like a version, noisy version of that dog. I go here to a larger unit, basically expanding it. So instead of doing it in one go, you gradually adding quality and improving the image. Right? So this becomes another version which has its own, again, all of this has pros and cons. But the basically generates much higher resolution because you don't go in one go, you repeat it from a small to large series of times, so you get a better quality, basically image, more like with more fidelity, basically. Now, wait. Oh, how did I pass this? I literally passed it on this one. So have you heard a stable diffusion? Yeah. So a stable diffusion is technically it's a version of the diffusion with the autoencoder, like the encoder concept. So this is a latent diffusion. So a stable diffusion is just a latent diffusion where you don't train the encoder with the basically with the diffusion. You just train it separately. So you train a really good autoencoder, which is job is encode decode, and then you focus is I have this encoder decoder done. My focus is to build a diffusion model that can go from latent, basically variable, from the encoder to noise and back to the latent. I don't need to care about how good is the decoder in generating the image, right? You see what I'm trying to say? So in the original version of the latent, you train this together. Autoencoder, diffusion, like encoder, diffusion, decoder. This trains together. Why we call it a stable diffusion? Because this wasn't stable. How we can stabilize this? We first train this, have a base model. We don't focus on that. This model works perfect. Every time I give an image, gives me this, and I can regenerate the image. So then I just use it as a data encoder for me. I give it data to it during the training, gives me a Z. I pass the Z to this diffusion, and I train this diffusion to give me back Z. I don't need to do that. I just need to be sure that the Z is like, so I don't train the autoencoder together, so that becomes a stable diffusion. All right. So Yeah, so that was it.